Okay, the next thing we have to talk about then is we're going to talk about pressure. And pressure is going to be a lowercase p that we're going to use here. And to discuss pressure, we need to look at an area. So here I'm going to draw an area. Surface area here that I'm looking at. Okay, and you're going to look at the force normal here. The normal force acting on that area. And pressure is going to be defined as the limit as my area goes to a very small area of the normal force divided by the area. So just like we looked at the densities, we're looking at smaller, smaller, smaller. The same thing's happening here with the area. We're going to a smaller, smaller, smaller until we can find out what that thing is at a point. At a point, okay? So pressure acts in all directions. If I have a point right up here, pressure acts in all directions evenly on that point. Evenly on that point. That's an idea that you'll learn more in fluid mechanics, but that's what we're going to apply here. And if we look at pressure on fluids in motion, that's going to be more fluid mechanics. And so a lot of things we can talk about that you have probably dealt a little bit about in physics, we're not going to discuss as much here in thermodynamics. I'm going to deal more with that pressure that you can measure and that value of pressure that given to you by a pressure gauge, a Bourdon gauge, a barometer, a manometer, something like that. We're going to look at that value, but you need to know how to deal with those things. So let's talk about maybe manometers a little bit. And I'm assuming in physics that's some of the prereq material that you have coming into here that you can know this. But let's go say we have a tank full of water. Okay, and this triangle here represents the free surface of the water. And if I want to find the pressure at this point 1, pressure at 1, we know that pressure at point 1 is equal to the density of that water times the gravity pulling on that water times the distance down to that point h. Okay, and we know that the pressure is the same at that point. All along this line is going to have the same pressure because it's the same distance down in a single fluid. Okay, now we also have coming up above this, we have the atmospheric pressure pushing down on top of this, so it's going to be plus P atmosphere, and that's going to give us the pressure at point 1. Okay, that's really what you need to know in this class. Now we might have, if we have multiple fluids, we have to deal with, let's just say we had another fluid up here pushing down here, we'd have to find out what the density times the gravity times the height of this fluid is, and we'd find the pressure at this point, and then we would add down to find out what the pressure is at point 1. Okay, very, very common thing for you to talk about in physics. I want you to know that in a basic sense. That's what we're going to be dealing with here. But moreover, we're going to be giving to you, I'm going to be giving to you pressure so that we can figure this out. So the main thing we have to know here is this idea I just talked about, but I'll write it specifically, that pressures at equal elevation on a continuous medium, non-flowing medium, are equal. That's what I said here. Everywhere along this non-flowing medium are going to be equal pressures. Okay, now, there are 3 different ways to tell you pressure. Okay, so the first way to tell you pressure is pressure absolute. Absolute pressure. This means this is the pressure with respect to the zero pressure of an absolute vacuum. Okay? Of an absolute vacuum. Now, This pressure here, this is what we'll be dealing with most often in thermo. Okay, if you don't know what the problem is given to you, they're given to you an absolute pressure. That's what you need to understand. That's going to be the default in thermo. But there are other types of pressures. There's pressure gauge pressure, and we could spell gauge two ways, this way, or we could spell it G-A-G-E. I don't care which way you spell it. And this is going to be the pressure with respect to, WRT, with respect to the atmosphere. Okay, and basically this is going to be above the atmosphere. Okay, above the atmosphere. Looks like I'm getting a delay here. I'm going to pause and see if I can't get this all figured out. Okay. So gauge pressure is something that we are we're using a gauge. So let's just think of this my service pin is a tire gauge. I'm going to go put this in my tire. I'm going to measure out what the pressure of that tire is. What that's doing is telling me what the pressure is above the local atmosphere. When I have it right here, this is measuring 0. When I'm putting it on the tire, it's seeing how much above the local atmosphere I'm at. Now, that depends on the local atmosphere. So if I'm changing from a bottom of a mountain to the top of the mountain, now my local atmosphere has changed, and so my pressure, the air in the tire may not change. I am going to be measuring different pressures, gauge pressures at the top and the bottom, because my local atmosphere, or what I'm considering as my datum, is changing. So that's important to understand. Now, there's another type of pressure called a vacuum pressure. Okay, vacuum pressure. A vacuum pressure is the pressure with respect to the atmosphere, but this is going to be below. Okay, and sometimes this is called a suction pressure. Okay, it's a suction pressure or vacuum pressure. Now, the one thing that you need to understand about this is, even though it's given below, this is always given a positive sign. It's given a positive sign. So even though it's below, we're going to say suction pressure and say it's positive, a positive sign, so that you know, you should know in your head, okay, I'm dealing with the suction pressure, that's going to be below, or a vacuum pressure, that's going to be below. So here's what we're going to do. I need to draw a little diagram for you. I think this is a good way to look at this. Okay, here is my 0 of a complete vacuum. Here's my 0 of a complete vacuum. If I'm going up, let me delete this line. I don't want that line. If I go up here and say this is my pressure, and I measure from this low point all the way up here, this is going to give me P absolute, or PABS. Okay. Now, somewhere along here, if this is going to be the local atmosphere, whoa. If this is the local atmosphere, and I measure from the local atmosphere up here to this absolute pressure, this is going to be pressure gauge. Okay? That's the difference. Now again, if we look at this and we say, here is going to be, this is going to be my pressure absolute. But I know that's below the local atmospheric pressure. If I'm going to look down and say, well, this is going to be now here, this is going to be my pressure vacuum. Okay, that's what we need to discuss. Now, because we don't want to, in thermo, worry about what the local atmosphere is at all, we want to make sure that we are dealing with standards. We are going to be dealing with absolute temperatures, absolute pressures completely. We don't want to ask, where are you at? What's the local atmospheric pressure? Know all of that information. We want to make it as simple as possible so every problem that we're going to be dealing with is going to have an absolute pressure. So unless otherwise stated in the problem, your problems are going to give you absolute pressure. If your problem doesn't say, if your problem says a gauge pressure, then you know in order to do your calculation, you're going to have to add the local atmospheric pressure onto that gauge pressure to find out what the absolute pressure is. Okay, so that is very, very important. All right, so let's write this here. P gauge is equal to P absolute minus P atmosphere. And we can do all sorts of calculations about that. Okay? Now, that being said, now let's talk about the units about pressure that we can work with. So our units. In SI, we're dealing with something called the Pascal. Okay? Pascal is going to be a PA. Pascal named after a person, so it's capitalized PA. And so 1 Pascal is going to be equal to 1 force, Newton per area, meter squared. 1 Pascal is 1 Newton per meter squared. But we often don't deal with pressures that small. We're going to be dealing with kilopascals. So 1 kilopascal is going to be 10 to the third newtons per meter cubed. And even higher in some things where we deal with megapascals. So 1 megapascal is equal to 10 to the sixth newtons per meters cubed. And so we're going to be dealing with newtons per meters cubed. That's wrong, Wanklin. You're probably yelling at me from home. Meters squared, we're dealing with force per unit area. Okay? Now, this being said, when we're doing all these calculations, we do need to know what an atmosphere is. And so a while ago, there was a discussion about what should we consider in our calculations what a standard atmosphere was. And so people got together and they made a discussion and they said that a standard atmosphere is going to equal to 1.01325 times 10 to the fifth newtons per meter squared. That was a decision of what a standard atmosphere was. So we can use 101.3 kilopascals. Okay, this is how I remember it. So in Manhattan, Kansas, there's a radio station that's 101.5. It's called K-Rock. I remember that this is 101.3, just right below it. And so my joke is, and I've told this many semesters, my lifetime goal is to be able to buy the frequency on the radio 101.3 kilopascals, and just in this voice that's butter that you can hear every time. You can just, when you're feeling sad, when you need a little thermo or something in your life, you can turn it to 101.3, and there's going to be a person on the other end saying, "Hello and welcome to a standard atmosphere, 101.3 kilopascal, broadcasting to you live all day. A standard atmosphere, 101.3 kilopascals." Over and over and over again. It would just be, I think it would be wonderful. No commercials, commercial free. It'd be a wonderful thing. And my lifetime goal is to do that. So I'm hoping that you get to see that. Now you might look at that and say, Dr. Wanklin, that number is so close to 100. Why didn't they just choose 100? And that's a good question. They didn't choose that for a variety of reasons. But it's often simpler for us to consider 100 kilopascals and to work with that. So I want you to know that 1 times 10 to the fifth has a special name, newtons per meter squared, because it's called a bar, B-A-R, a bar. So in SI, we have another unit of pressure called a bar, which is 1 times 10 to the fifth. That's what we're going to be working out. So know that is a bar. So there are all sorts of times where we're going to have to convert between bars and kilopascals. In fact, if we go back to our document camera, it's so popular that here in the corner of all of our tables, there's going to be a pressure conversion here between 1 bar between kilopascals and megapascals. That's probably be easier to see here. See how it says 1 bar? That conversion is going to be there all the time for you to look at. So that's important for, it's an important thing for us to work with. Okay, now in English engineering units, we're going to be dealing with something called pounds per square inches. Pounds per square inch. Now the question students often ask me is, which pound is this? Well, you have to understand what pressure we're talking about. In pressure, we're talking about force per unit area. So this is going to be pounds force per inch squared. Okay, this is what it is. Now, we're also going to call this PSI. If you see me saying PSI, I'm saying pounds force per inch squared. And this is a very important point that you are going to need. If you have a calculation which has pounds force and also has pounds mass in it, here is where you're going to need to do that calculation, that conversion between pounds force and pounds mass in your calculation. Because sometimes you're going to be taking these things and you have to work with them. And so it's important that you know that you just can't just use them interspersingly. We'll use that word. That's a ridiculous word, but I made it up. And we can't just use them back and forth. We have to make sure that we convert between those two. From time to time, we're going to do pounds per square inch. Pounds per square foot, but that's not going to be very common. But pounds per square inch is going to be your most common one. Standard atmosphere. Is going to be 14.69 psi. I just use 14.7 in my calculations. It's close enough. We can also do 760 millimeters of mercury. I should have done that earlier. Millimeters of mercury, or 29.92 inches of mercury. Okay. Now we will say, and this is another thing I need to show you in your conversion factors. Let's see here, in your conversion factors of your textbook. Get to that and go into the document camera. Here in the very bottom corner here, there's going to be standard atmospheric pressure. It tells you how many bars, how many psi, how many inches of mercury. So note that that's always there ready for you. Note that I'm going to go 101.3. I'm going to do 14.7. Those are going to be applicable in your calculations when you're dealing things with Wiley Plus. Okay? All right. Now, from time to time, you will often see, if you see PSI, you can assume that's pounds per square inch absolute. Absolute. But sometimes, to be more precise, sometimes people say PSI-A. This A means absolute. Okay, but if you don't see the A, you're going to assume it's absolute. If you see PSIG, what do you think that means? Of course, that means gauge. This G means gauge. And so you are going to have to add the atmospheric pressure to get absolute. And so I am going to make a big note here, and I'm going to use my rainbow color because it's so important. Pressure absolute must be used in all thermodynamic calculations. Okay, very, very important. Okay, that ends our discussion about pressure.